Jose Bogus and Robert de Jong, and for today's talk, I'll assume that we're over a ring with two invertible. The complex numbers is fine. If you want to do characteristic 2, then we can talk about it. Okay, so this is a conference on moduli of abelian varieties, and I guess I get to define this. It's a great privilege. And so I'll put a little dash here. So what this is, of course, A of S is an abelian variety of relative dimension G, and lambda is a principal polarization. And so the weird thing, of course, is that I've got this line L, so L is supposed to be a line bundle on A, which is symmetric and which is representing the polarization. So L on A is rigidified. It's symmetric. Okay, so it represents lambda in the sense that lambda of little a is the usual formula. Okay, so there's this sort of funny thing where a polarization on a variety in general is an ample line bundle, and the polarization on a abelian variety is a map to the dual, or an isogeny to the dual, which is locally representable by a line bundle. So what I'm doing is I'm saying, well, I'd like it to be globally representable by a line bundle. Okay. And so maybe
put prime there. What?
Yeah, well, the prime is because of the L. I mean, I don't know. Normally people would. So this is a degree 2 to the 2G cover of the usual AG. So if you forget the line bundle, then that maps to usual AG, and this is a degree 2 to the 2G Etal cover. It's a torsion with a torsion. So I will talk about why I'm doing this. Maybe, so symmetric just means that -1 alpha star of L. And really this rigidification and the symmetry are extra data associated to L. Okay. And so over this thing there is a universal abelian variety, A or something like that. And so the point of this setup is that this guy now carries a polarizing line bundle and carries a theta divisor. So A carries polarizing line bundle. Is this L, and this carries a theta divisor. And there's also, of course, a Poincare bundle. And so if you do usual AG without the prime, then you have the class of theta in Chow with rational coefficients, the class of this theta divisor. But I want an actual divisor because I want to talk about extending this divisor to the boundary, which is why I'm adding this extra data. And so this line bundle and the theta, these are sort of ways of capturing the polarization, and they have various properties and relations between them. So we have that. So L is very closely related to theta, so L is O of theta. It's almost O of theta, but O of theta isn't trivial along the zero section, so theta minus pi alpha star of theta. So fiber-wise, L is just O of theta. L squared you can get from the Poincare bundle. So if you pull back the Poincare bundle along the diagonal of A times A, then this is 2L. If you don't like this sort of inexplicit term, then you can make it more explicit. 46 squared. This is the determinant of the Hodge bundle. Some other nice properties these have. So because L is defined to be symmetric, it means it's pure of weight. So that means for every positive integer n. I realize I'm using some notation that I didn't define. So generally, if I have an integer in brackets, abelian variety to itself, this is just multiplication by n. So I'm using that here already. Okay, so this line bundle is 2, that follows from symmetry in the theorem of the cube. And this Poincare bundle isn't just a random line bundle, it's a bi-extension. And so I'm not going to, I don't know, it's too early in the morning to talk about bi-extensions, I guess. So we'll just say this. If you like bi-extensions, then it's great. If you don't, then you can just ignore it. And I mean, I could continue listing various other properties and relations, but to me this is sort of the main thing that ties these guys together. And so this is all over AG, and so what I want to do is to extend this to AG bar, so some toroidal compactification. Extend maybe even this package of things gets a extend this star thing or to the universal abelian variety. Okay, so I'm assuming that people are reasonably happy with toroidal compactifications of abelian varieties and universal abelian varieties. If not, I guess you should shout at me. But I'm taking that we're okay with awesome. Otherwise, I have to improvise very efficiently. So I've got the theta divisor and this line bundles, and I want to extend it to toroidal compactification. And the only toroidal compactification I know, these all live upstairs on the universal abelian varieties. So I need to compactify both of these in a sort of compatible way. And the only way I know how to do that is this: put the Voronoi here and the mixed LNA Voronoi here. So if you know a different way, then you can choose that way, and I think the talk will still be true. But this is the only way I know, so that's sort of what I will assume. So when I write AG bar, that's the guy I refer to. So we have sort of standard extensions. So the line bundle adds a bit of an awkward one. So call this L bar. This is something constructed. So the machinery that gives you this mixed LNA Voronoi compactification, or more precisely proves that it's projective. You read Falting's Chai or Mumford, and they tell you how to do this. So it's from Mumford. To those who've seen it before, great, it's very useful. If you haven't, then it's a thing that you can do. The theta divisor is more satisfying. You can just take this risky closure. So this is part of the reason I wanted to have an actual theta divisor rather than just a class, is because the Zariski closure is then a thing that makes sense. And the Poincare bundle, there's, again, theta of that line. So from Mumford, Falting's Chai, they will tell you how to extend this Poincare bundle. And if I look at my list of things I want them to satisfy, then the first three are kind of okay if I put bars everywhere. But the last two completely fail. So this line bundle extension is not pure weight 2, and the Poincare extension isn't a bi-extension. This guy is not pure. And so those are the two things that I want to fix.
Hey David, can I ask a question? So you're saying second Voronoi or whatever, one of those things?
Yeah.
I'm used to that being on AG, actually.
Yeah. Wait, you mean, are you worried about the fact that I'm doing the universal or the prime?
No, the prime. Yeah. So what happens over the?
So for the second Voronoi, you decompose the space of bilinear, symmetric bilinear functions. For this one, instead we look at the space of quadratic functions, integral value quadratic functions. So it's a slightly different lattice structure, but over Q it's the same. Okay. So it's a very
it kind of ramifies in the loggy way over.
Exactly, and so you have to be a little bit careful with the integral structure when you say what it means for a decomposition to be smooth, but otherwise it's the same. There's this sort of two-page section in Falting's Chai about theta level structures, where they sort of vaguely sketch how to do this. And then for the rest of the book, they assume that you worked out all the details. So it's a bit of a weird situation, but it sort of, morally speaking, it just goes through the same.
Thanks.
One thing you can do is you can just pull back. You can just sort of, normalize this in, what do? You normalize AG bar in this thing, and that gives you something, but that will generally be very singular. So it's better to do this sort of
Sorry, so again, so A bar is the universal semi-abelian variety? Is that, what was A bar here?
A bar is bar really means a proper thing.
Okay, so you've compactified it further.
By choosing cone decompositions in a suitable way.
So before asking questions, what is a bi-extension?
This is the question that I don't want to answer. So basically, so
Don't answer it.
yeah, so roughly speaking, what it means is that P, so it's a function of two variables, A1 plus A2B, comes with an isomorphism to PA1B tends to PA2 comma B. And then that's also true in the other factor, and these are all compatible. So somehow it gives you a way to sort of a group plot on the fibers in some sense. It's some long definition in SGA that I don't want to.
What do we care about it being a bi-extension?
So the fact that it's a bi-extension is kind of the whole thing that makes it useful in some sense. I mean, sorry, that's a very silly thing to say. So, well, one option is forget the whole bi-extension thing, just think about pure extensions. But also, I mean, yeah, so... For example, things like the theorem of the cube, which are fundamental important things, basically correspond to this kind of statement. So the fact that you can, I said here that there is a relation between, you can write P in terms of L, but you can also write, you can write L squared in terms of P, you can also write P in terms of L as this P is M upper star. So P1 upper star of L dual. And the theorem of the cube for L basically corresponds to the bi-extension structure here. And okay, so I will say it's basically it's an incarnation of the theorem of the cube, and then I will declare this to be an important thing, and that's my answer.
Sorry, just to clarify, so it is the pullback of the second Voronoi fan from AG, or no?
Well, everything I say should be pretty much independent of the choice, but technically no. Like there's a natural way to refine it on this AG prime thing.
Because the integral structure has changed.
The integral structure has changed. Indeed. Sorry, yeah, we can have a sort of carefully writing down Cohn's conversation, maybe. Okay. Any other? I like this hour and 15 minutes. We can just take our time. Okay, so for the moment, let's pretend at least that we've agreed on some compatible compactifications here. Yeah. So the theorem is that you can fix this. So there are extensions which I will call theta pure, L pure, and P by extension to A bar over AG1 bar. Sorry, AG bar. There are ways which satisfy all of star. Okay, so the line number L is pure of weight 2, and this, so L pure is pure of weight 2, hence the name, and P by extension is a by extension, etc., etc. So these extensions exist, and they're related to and they're unique with these properties. They're related to the previous ones. So essentially they're related by tropical theta functions. So theta pure is theta bar, the Zariski closure, plus the divisor of some tropical theta function. L pure is just the old L bar twisted by, again, a tropical theta function and the Poincare by extension thing. And this is twisted by the tropical monodromy parent, whatever that is. So I won't talk about this, so we should just ignore this line from now on. But we'll talk a bit about these tropical theta functions later on.
So you don't have to subdivide to make this.
You do have to subdivide to make this happen. I think what I haven't told you is what any of these things... So what I need to tell you, and what I will spend the rest of the talk doing, is where these live. What is, yeah. So these are not what kind of objects these things are, and what these tropical theta functions are, and what all these symbols mean, none of which I've defined.
No, but I'm saying you drew a bar over AG.
Yeah, those are wrong letters.
Those are, now you've changed what bar means, right?
And also AG bar.
I haven't changed what bar is, but I've changed what
You just change what extensions mean.
yeah, I mean, this isn't a divisor in a naive sense, and this isn't a, this is not a naive kind of divisor, this is not a naive kind of line bundle.
It's much worse.
Okay, but so I guess my what I was, okay, so my guess, maybe to explain where my question came from, my guess was that you were going to write down some piecewise polynomials on a admissible decomposition and twist by those. But now you're telling me you're going to do it on the second Voronoi?
No, I'm telling you that I'm going to write down something that's worse than piecewise polynomial.
Okay. I got it.
Essentially, answering your question is what I will do in the next.
Okay, good.
Hopefully. If not, then please ask again. We'll see if I.
But you said all of the above, so multiplication by n, that will stay like this? I mean,
Even to
you
define
have to define it.
This is next. Sorry, maybe this was. I was trying to be too cool. Maybe I should have been. Maybe I should have first defined the thing before stating the theorem. Would that have been? We'll see.
No, this is cooler.
It's cool. I mean, yeah. Anyway. So, I mean, nobody likes by extension. So let's talk about this pure thing, multiplication by n. So what does pure mean? So what are compactifications? And so, I mean, let's say we just have some sort of, I don't know, we have A inside A bar, any old toroidal compactification, and then we have some line bundle on A bar, and what does purity mean? So I kind of repeated what I did here. So, I mean, on the abelian variety itself, we've got a multiplication by n. On the compactification, this is at least a rational map, which are still called multiplication by n. I don't know how to pull back line bundles or divisors along rational maps, so this isn't good enough, but of course I can blow up to resolve this thing. And now we'll call this honest multiplication by n. So what you could ask for is something like that, well, n star of L, by which I mean now this, sorry, I've got three maps called n. I'll call this with a little tilde. So the pullback along this thing should be something like L upper star of L. That's n square, n to the d. So this would be a reasonable thing you could ask. And I guess you'd have to ask this for every n. And at least morally you should also, I mean, in a compatible way somehow, it's a little bit nasty. So you can sort of make sense of this. The problem is that these don't exist. So this sort of makes sense, but they don't exist. So if I really try to do what Sam wanted me to do and have an actual honest line bundle on here and have it satisfy this diagram for every n and every choice of tau, then I can't do that.
Well, I would actually want more. I mean, you are only resolving the map one way. This is a morphism, so you could try to resolve it both. I mean, you could try to blow up both the source and the target.
I mean, this diagram exists.
Sure. But
The L doesn't
try
exist.
to blow up on the right.
Yeah, indeed, I can, yep. Doesn't help.
Does it exist for if I pick an n? Is it the for all n that's important?
Question. Well, I mean, n, okay, excluding n is 0. Can you do this for n is 0?
It will never happen. Basically, it will never happen.
Yeah, I'm suddenly hesitating about my super categorical statement that there's no n which will ever happen. I think the problem is that, morally speaking, when
Yeah, sorry. Yeah, that's thanks. Yeah.
okay, so the question is where should all this? So I somehow claimed that there's no there's no divisor or no line model for which this will work, and so I want to, I have to do this.
You might slip.
What's happening? It's a flooded back.
And now there's a television just behind where I'm throwing the This isn't designed for foreigners, I think.
Can someone take a photo of that?
I don't think we've had anyone injured lecturing before.
There's always, yeah, I'm happy to be a volunteer.
Insurance.
Somehow this board is very clean. It doesn't look like people have been covering it in chalky water for years, or the cleaning is very efficient.
Yeah, that's good.
So I want to talk about like different sort of. I said this doesn't exist as a line model. Okay, it should be some sort of like fancier gadget. So I want to talk about the options for fancier gadgets. I want to perform a sort of sleight of hand, and I want to talk about divisors instead of line models for a moment. So, I mean, you can make the same story for divisors. You can say, well, if I have a Cartier divisor in here, I can ask for it to be pure, and the problem is it doesn't exist. So I'll talk about divisors, and then we'll come back to line models in a moment. And this is because I think that many people here have seen some of these sort of log intersection theory or Zhao type things. So this is to make more sense for these people. If it, well, we'll see, maybe it will crash and burn. So various kinds of log divisors. Okay, so I've got some nice log or toroidal variety, toric variety, or whatever your favorite category is. And then there are various notions of divisors on this thing. So we can sort of literally look at divisors on X. Or there's a bigger thing we can look at, which is log divisors on X. And this is defined to be the co-limit over all log blowups x tilde to x of the divisors of x tilde. And so the way I want to think of this is that I think of an object of this as being a pair of some toroidal blowup of x and some divisor on that toroidal blowup. And then I will say, well, things are equal if they become equal on a common refinement. So I take this big collection modulo and equivalence relation. And this I want to call the small log divisors. And
So the transition maps are total transforms, not strict transforms, or
yeah.
You demand that the divisor, like, that it's be Cartier, essentially, that it's at finite level determined.
Yes, exactly. The co-limit thing says exactly it's an equivalent. It's represented by some divisor on some model. But then there's as perhaps what it's hinting at, there's a. Well, you're anticipating.
This is too small for David.
So there's the other version, which is the big one, the big log divisor group, which is the limit of x tilde to x of div of x. So here the limit is on push forwards. So this I want to think of as I give a divisor on every single model and they should be compatible. Thank you. I give a divisor on every single model and they should be compatible under push forward. And the projection formula tells you that there's a natural inclusion of this into this. If I'm given a divisor on some model, then I can pull it back to refinements and then push it down. And so that will, I can go from one of these to one of these. Okay.
And these, it's the blobs don't have to be non-singular and on the right-hand side.
It doesn't matter. And yes, maybe let's just always restrict to non-singular blobs for simplicity, but it shouldn't really change the answer, I think. Yeah, if I want to be pulling back, then I should say non-singular or Cartier, but the non-singular cofine also should be okay. And so we're trying to decide sort of where our theta bar should live, and so the idea is that, what can we say? So we can ask questions about these things like, is it independent of the compactification? Well, that's a silly thing to ask, of course, the way I just set it up, because I gave myself an x. Morally speaking, we're going to apply this to this universal abelian variety. And so we can ask, well, does the answer depend on which compactification we chose? And of course, in this one, yes, because it's really the divisor on x, but all of these other ones are independent of the choice of compactification. So this is kind of handy.
No means what?
Yeah.
It's independent.
Oh,
yeah.
That means, that means yes and yes. In my notes I had ticks and crosses, and then I realized that the crosses look like X's, so I was like, oh, I'll switch to yes, no. And there was somehow a slight parity, a sign error came in there. Fantastic.
Can I ask, so do we have like, is there like stable notation for small log div and big log div?
There was before certain people used it for something. So I used to.
Sorry, I don't know who you're subtweeting here.
Log cohomology and log homology.
Right, so this was cohomology and this was homology,
Yeah.
but then there's a paper of which you're an author which uses homology to mean something different. So now we're all in trouble. But I think this is like the cohomology thing and this is like the homology thing. But then there's this paper by Dhruv and Rahul and Johannes and Pim, right, where they use this homology to mean something different. So I don't know. I mean, I'm a bit stuck now. So I'll stick with big and small. And the big small has a nice. It'll work well later on. So
Can I ask what we use the homology to mean? In
you used homology to mean this thing, but where you put the Chow homology instead of the Chow cohomology, which matters when you're doing these very nasty, like idealized log smooth things, which you were doing.
So it's pretty reasonable.
I mean, it was a So I mean, because it's like a good idea at that time. Yeah. I mean, so here, of course, I'm being naive from divisors, but you can put like Chow or something. And if X is singular, you say, well, do you mean Chow homology or cohomology? But then you can do like the limit or the colimit of the homology or the cohomology. It's just kind of awful.
But in that paper, we thanked David for suggesting this.
Seriously? Wow. But suggesting the notation specifically? Yeah. It's getting increasingly embarrassing. Okay. So I'm supposed to be talking about theta. So contains fewer classes. So I sort of mumbled about the fact that usual line bundles, divisors, whatever, with this definition of purity don't exist. This notion of purity makes sense very happily for either this group or for this group. I mean, there's still things that you can pull back, it's all fine. So you can ask whether or not you can find pure classes in this sense or in this sense, and the answers are, well, I said no here, and it's again a no here, and it becomes a yes over here. Okay. So these pure extensions do exist as these kind of very large, in this big log divisor or big log Chow group where you allow things to, what do I want to say? So somehow this says, like, if they existed here, that would say, well, as long as you choose the right model, you can find a pure line model on that model. Whereas what happens here is it says, well, you choose a model, for any given model, you can find a thing which is almost pure, but then when you do this kind of pullback procedure, you'll have to change it a little bit. And then when you blow up again, you have to change it a little bit again. So these are sort of things that never stabilize. And so this is where these pure things live. And so this is in some sense the theorem, or version 1 of the theorem is that they live in here. Well, there's, in some sense, there should be a reason why we're doing all of this. And while I won't talk about it today because I can't, I don't know anything, but we'd like to do things like intersection theory.
Sorry, is it obvious that the answer is no for the small one? It's no.
I don't.
I mean, it's kind of clear because that being a finite blow-up where all of these maps n exist for all n, it seems that.
Yeah. So morally, I mean, it's sort of clear that it shouldn't really exist because, as Rahul was saying, like, every time you do this, you keep changing the model. So it feels like the model should keep changing. You could argue, well, maybe you get lucky, but it turns out that you don't. I mean, this thing is injective, and as soon as we start to write down these guys, we'll see that they don't have an image of this.
But even if I just fix n, and let's say it's bigger than 2, even then maybe I would expect it not to exist on the small one.
I think so, but I haven't thought enough about fix a single n question. So the reason I haven't thought about fix a single n is because you generally, with these things, you want to do some sort of dynamical system thing. And so normally you'll end up like pulling back again at some point. And that's essentially taking n squared. And so, yeah. But I mean, it's a fair question. So can you do some kind of intersection theory? Well, here, yes, and here, yes, and here, definitely no. So we're in this sort of awkward situation where we can write down the pure classes in this horrible thing, but there's no notion of intersection theory, so it's not particularly useful.
But how do you get your hands on something? How do you write down something?
That is the next slide. Yeah, very good. You're asking all the right questions. So maybe I should also, for context, add an extra row. I'm going to be pedestrian. Sorry. For people who have been following like this log_dr story, so log_dr contains, and this is a no, and then a yes, and a yes. So in some sense, this small log tail is big enough to contain log_dr, but it's not big enough to contain these pure classes. That
This would be like, instead of going for piecewise linear, you have to go to like continuous functions, like some limit of piecewise.
exactly. Very good. You're
Can you repeat the question and answer?
Uh,
You'd rather not.
I will repeat it in more detail very shortly. It was about like somehow taking continuous. Also, because I would. The answer, I guess, is kind of. I will get to it in a moment. So basically, this is sort of an unsatisfying situation where the pure things live in this thing that's too big to be good for anything. And so what we want to do is we want to read this paper by Yuan and Zhang on adelic intersection theory, and we want to add another column in the middle, which I can call medium log chow. Medium. This is why I'm glad I didn't go for the 12 line or smaller. What's half of the Okay, and so how do we define this? Well, we take the small one, and then we do the completion in some sense, which I will talk about in a moment. Okay, so here you've really got a fixed model. Here, completely wild stuff can happen. As in here, sort of when you blow up, you introduce a new exceptional divisor. You can put any random coefficient on that new exceptional divisor. And so these are really wild. In these ones, when you blow up, you can put the new coefficient on the exceptional divisor, but you can only change the pullback by like a small epsilon in this completion. And so...
Can the epsilon get smaller, or is it keep...
Yeah.
So sorry, small log and log small are the same.
Yeah, small log and... Sorry, this is meant to be a copy of this. Yeah. And so this one is independent of the compactification, contains pure things, and there's a reasonable amount of intersection theory. And of course it contains this guy. So the claim is that this column is a nice place. The star is because I'm only talking about divisors. And so it's not completely, well, there's a couple of reasons for the star. Firstly, this is only divisors. This isn't chow at this point. So intersection theory, let's say that we just mean take a top intersection and get a number out at the end. And this works here.
Yuan and Zhang do have intersection theory, right?
Yes, but they don't have a whole chow ring. They have, I don't know, yeah.
If I were just doing, let's say, actual cohomology and homology, would the situation be easier in higher codimension?
That's a good question. I don't know. I'm a little skeptical, but maybe. Another thing is that you actually have to very slightly, like, just the completion, there isn't intersection theory. You need to very slightly restrict in a way that's harmless for what we're doing. Anyway. Okay. So, what am I doing now? Okay, so I talked about taking the completion, and so I have to tell you what metric we complete in. And this is not, it's not quite a metric, right? It's a uniform structure, which according to Wikipedia is what you need to define completion. Oh yeah, I should say, I should write this on the board. This is, so this idea of taking this completion, this is an idea of Yuan and Zhang. So what do I mean by completion? So I have to tell you when line Monroe divisor is small. I feel like I've never made quite as much a mess of this as I am today. So the metric, the uniform structure. So we have that our x bar is really, I think of as a pair of x bar and d, where this is a boundary divisor. So I really think of it as a toroidal or something guy. Say a divisor E some model x tilde is small if, on the one hand, E is fixed to 0 on the interior, on the other hand, it's trapped between, it's basically sandwiched between the pullbacks of this guy. Of course, I've totally failed my analysis 1, right? This isn't how you do quantifiers, but I hope the idea is clear that the small ones are the ones which are trapped between small multiples of the pullback of this divisor. Sorry for the failed quantifiers. Okay, so this gives me a notion of small things. It basically says that when I blow up and I pull back, and then I can change by a small multiple of the exceptional, and that multiple sort of shrinks as I go up the tower. Okay. And so this is a thing that one can do. And so a question that Rahul asked is, how do you write down elements of any of these three groups? And so, of course, I mean, writing down divisors on X, that's sort of your problem in some sense. I mean, if X is 80 bar, then you're writing down arbitrary classes on that is hard. I'm not going to manage to solve this. So I'm just going to assume that sort of within reason we know how to write down divisors on X. Okay, so what are we going to do? So we've got X, which is our nice toroidal, maybe a toric variety, something like this, and we've got X trop, which is a cone complex. Or a cone stack, or an Artin stack, or your favorite category to work in. And so, how do we write down some elements of these things? So firstly, there's a map from so if I have a piecewise linear function on X trop, so S for me means strict. So these are strict piecewise linear functions on the cone complex are the piecewise linear functions that are linear on each given cone. So this is the most restrictive sense of piecewise linear functions. If I'm given such a guy, then what I can do is, well, I just look at the values on the rays. So the rays of the cone complex correspond to the boundary divisors here. I look at the values on the rays, and that gives me a divisor. So I guess formally I can write this as, so rho is a ray in X trop, and it's F primitive here, times the class of the divisor corresponding to rho. So this is a perfectly well-defined map that you can write down. This will get a little star next to it. Well, that's a way to write down some elements of div X. Of course, these are all boundary classes, so they're not super interesting. How about these small log divisors? Well, we should remember that so subdividing the cone complex corresponds to making toroidal or log blow-ups of X. So we can look at all the piecewise linear functions on X trop. So now they're strict on some subdivisions. And this maps to this small log divisor of X. And what do I do with the function F? Well, I say first, find me a subdivision where it's strict. And then apply the first recipe. And then one has to check that it's independent of what choice of subdivision you make. Of course, any finer one will do as well, and that these things actually are compatible under pullback. But these are not hard things to check. And so we've done the left two. The big group, how do we write the elements of this thing? Well, notice that what we used here was really only the values on the rays. So supposing we have a function which is just only it's linear on the rays and we know nothing else. So I'm going to call that a conical function. One of those guys will determine an element of this big log Chow group. So there's no kind of continuity needed. Just any conical function on the cone complex will find me some element of this big log Chow group. But it's kind of a mess. Like my order, I think. So we can continue the story and we can say, well, conical functions are sort of big. Big dividers and sort of weight. So conical, I just mean a function that's linear on each ray.
But after some subdivision.
Sorry, linear on every ray to every
Oh,
rational
every,
point.
yeah, okay.
Thank you. Yep.
Every possible ray.
Yep. We only actually care about the values on the rational points. To say a linear function on the rational points of this, but sorry, a conical function on the rational points, but it doesn't. So now we have to say what to do on every x tilde. So given x tilde, restrict to the rays and apply the recipe in the first place. And so because pushing forward forgets what happened on the exceptional divisor, this will always give you a collection of things which are compatible on the push forward. Okay. And so in the end we can make ourselves sort of a nice diagram of things. So we have strict piecewise linear of x drop, includes into piecewise linear of x drop, includes into the conical functions on x drop. And these all map down to the divisors of x. And the small log divisors of x. And the big ones. And these are all compatible. But again, we want to put the medium ones in the middle. And at this point, it's probably not at all surprising that we're going to impose some kind of continuity on these functions. And so, let's just do that. So inside here, you've got the continuous conical. These are continuous functions. And so this turns out to be, these map to this medium divisors of x, and everything is again compatible. And this is not really difficult to see, and the point is that if you take the definition of the metric, if one writes it down a bit more carefully, then what you find is that it's really just the metric of uniform convergence on these functions. And of course the limit of piecewise linear things under uniform convergence is continuous things, and so this is what comes out. Okay. So this is where maybe the little star about intersection theory comes in. So if you literally just take all continuous functions, this is a little bit too big. So I think the first version of intersection theory were defined on convex functions, but this is a group thing, so you can also define it on any difference of convex functions. And I think piecewise C2 is maybe the sweet spot for what kind of functions you want to allow, but anyway, so you should restrict slightly what continuous functions you allow, and then you have a reasonable intersection theory. Okay. So it's some group which has a reasonably concise definition, and we can write down elements of it in a reasonable way.
Where does the intersection product take values? Is it in the reals?
Sorry, just back to the higher codimension thing. So here everything is kind of linear along the rays. So if I did quadratic along the ray, what would happen if I
So the problem with that is, so this part works fine in higher codimension, but if you try to go here, then secretly what we're using is that if you have a piecewise linear function, gives you divisor on some subdivision. If you push forward, you're basically forgetting some rays, and that corresponds to just forget the values on those rays you missed and then linearly interpolate. But for the piecewise quadratics, there's no analogous procedure. You have to look at what happens instead of on the rays on the on the two-dimensional stuff. So there is a proposed version of this, like what should replace the continuous conical functions for higher codimension things that Pinfulia has written down, and it's sort of some mixture of a function and a measure, sort of an intermediate dimensional measure on the cone complex. But he sent me some notes, and I was checking my email last night, and he sent them to me in 2003, so I don't know if he's thought about it since. I think there are things to say, but this...
Did you say 2003?
2023.
Oh, sorry.
Was he born in
Yeah.
You were like 5th grade.
So I think the question of what you do here in higher codimension is super interesting, and we have some ideas, but it's not yet a very nice uniform theory of these things.
So is it the piecewise C2 thing that makes the intersection numbers converge as you pass to higher models?
Yeah, so one way to think about the intersection of theory is just, well, approximate it by these guys and then hope that the limit makes sense. And then piecewise C2 seems like a sufficient condition to do that. So, one thing that I want to talk a little bit about is this is unstable. I talked a lot about the case of divisors, but I mean, this purity is really more natural for line models, maybe. So what is the line model version of these things? And so, just describe that briefly. And so the line model version is also very nice if you want to do cohomology or whatever. And I'm just going to apologize. I'll briefly get technical and talk about log stuff more. So sorry about that, but I'll sweep down the carpet again soon. So the line model version. Maybe this won't fit neatly in my table. I don't know. So of course, line bundles on X we are familiar with. But there's a very silly way to think about line models in X, which is that they're pairs where L is a log line model and C is a strict piecewise linear section of the associated tropical thing, or the associated G-trop torso. So this is a sort of a very complicated way to write down a very simple thing. The reason I do this is because it naturally generalizes to these other cases, which I totally don't have space to write. So I'll just go down here. So what happens here? Well, for the small log chow, it's always the same. We just look at pairs of L, C. L is exactly the same, and C is a piecewise linear section of the tropicalization. For these guys, it's basically the same. It is L, C, where C is a continuous conical section. Over here, as I'm sure you've guessed by now, it's pairs L, C, where C is a conical section. Okay, so this gives a very explicit way that you can write down these objects. And I mean, the tensor product is just tensor the log line bundles and add the sections, so this sort of works in a reasonable way. So if you like log line bundles, then this is a very elegant way to write them down. If you don't like log line bundles, then I'm sorry.
Sorry, when you say a log line bundle, you mean, again, something that lives in this kind of direct limit of just pick?
Sorry, by a log line bundle, I mean, I now have to do honest log geometry, so this thing has a sheaf of monoids.
I see,
and I force it under the groupification of that sheaf of monoids. And actually, sorry, maybe I just don't want to, this is a bit sketchy. I'm not sure I want to do it.
Like Jonathan's.
Actually, Jonathan and Sam's log line bundle thing. You can also, well, I mean, you can give concrete definitions of these. Well, pick, we know how to define the Picard group. This, you can think of it as pairs of a model and a line bundle modular and equivalence relation where the line bundles are isomorphic under a pullback. And this you can define as a completion of that. So you can define these without any log nonsense. The log nonsense is very good if you want to actually write them down. Otherwise, this is just elements of the completion of some group we don't understand. Okay.
So did you just say what the comparison with log line bundle is or not?
So I thought I attempted to. Should I say it again? Differently? So what I want to say is that to give an element of this medium group in particular, what you should give is you should give a log line bundle, and you should give a continuous conical section of its tropicalization. So you tropicalize the bundle and you get some G-trop torso, and then you should give a continuous. So there's a notion of a conical section of a G-trop thing, and you should give one of those. So as in you can define the sheaf of conical functions on a Artin fan, and then you can tensor your tropicalized bundle with that sheaf of conical functions and take a section of that thing. We will see.
But for your theory at the beginning, you owe us like a continuous function, like some canonical continuous function.
You're extremely good at anticipating.
Yeah.
Yeah, this is the next thing. That's this tropical theta function business. Right, so somehow what's missing in all of this is I have to now tell you some, well technically I should tell you some log line models, but it's more fun to tell you about continuous conical functions. And so these continuous conical functions will be tropical theta functions. And so this is this is a reasonably old and well understood story, but we will have to change it a little bit. Because those of you who've come across tropical theta functions are probably familiar with the fact that they're piecewise linear functions. And so, okay, piecewise linear are continuous conical, but if that was what I was going to write down, then I could have given a much shorter talk. Okay, so a little sort of reminder. The theta, so recall that we have this theta pure, with this risky closure of theta plus the divisor of some tropical theta. And so, I mean, this tropical theta function is going to be a continuous conical function, and by divisor I just mean apply the procedure that we talked about here to go from a function to an element of this low channel. And L pure. Yes. Again, twisted by theta trop. And so this one we have to be a little bit more careful because we shouldn't just take, so Mumford and Fortingshire tell you how to write down a line bundle, not a log line bundle. And so you shouldn't just take the associated log line bundle. So if you want to apply the description given here, you need a log line bundle version, polarizing line bundle. So that is supplied by Kato, Kashiwara, and Nakayama in Log Abelian Varieties Part 7.
How many parts are there?
I think there are sort of 8, but 1 and 8 aren't called 1 and 8. They have other names. Morally speaking, there are 8.
It's like Star Wars.
Better. The character development is. So I owe you a log line bundle, but I will defer to KKN. I also owe you a function. Okay, so the theta trop, the tropical theta function. And so these were first introduced, I think, by Mikhalkin and Zharkov. So what they said was, well, take the usual definition of the theta function just as a big power series, and then you do this max plus thing where you turn the, am I even going to get this right? You turn the sum into a max and the products into pluses, and you get something. And then you observe that this gives you a piecewise linear function, and its corner locus is sort of a tropicalization of the theta divisor. So that's really nice, but it's not what we want to do, because we want continuous conical functions that aren't piecewise linear. Otherwise, shorter. And so I can give 2 definitions. And so the first one is horrible, but sort of useful. So AG1, so this universal abelian variety compactified, its tropicalization has a universal cover thing, which is so what is this? So Q of W, so W is a lattice of rank, sigma is G, Q of W is the integral valued quadratic functions on the lattice. And so if you're familiar with the sort of the usual tropicalization of AG, then this is a little bit different in 2 ways. The first is that I got this W dual part, a linear part, but this is just because I'm doing the universal abelian variety. So this is the fibers in this guy. And the other difference is that I'm doing quadratic functions instead of bilinear forms. And so that's because I'm doing this thing where I've chosen a polarizing line bundle. If you just want to get the bilinear form part, well, to any quadratic function, you can extract a bilinear form. And so you just do that procedure. So this thing maps naturally to the corresponding thing. So we have this
positive definite or positive definite quadratic?
positive, oh, good point. Positive semi-definite with radical on which the linear function vanishes. Yeah.
But if you put rank smaller equal to G, then it's
Pardon?
and if you put lattice rank smaller equal to G, then you make it positive definite.
So the smaller equal is because you want to glue these things, you want to glue these things along the smaller lattice things. But then you still have the semi-definite condition on these smaller. Anyway, yeah. You're the boss of these things. I'll just do whatever you tell me, but this is the okay, and then I can just write down this tropical theta function. So if Q is the quadratic function and L is the linear thing, then I can write a formula, which is very unhelpful. Okay, so what on earth does all this mean? So Q is a quadratic function, B is the associated bilinear form, so the bilinear form taking two inputs. B Q star is the dual bilinear form, and I'm only giving one input, so I mean evaluating one. And then there's this row thing, and so the thing is that essentially what's the difference between a quadratic function and a symmetric bilinear form? It's that the quadratic function doesn't have to be symmetric around 0. And so rho over 2 is exactly the place where the quadratic function is symmetric. It's a symmetry point. Of the quadratic function. Okay, so this is a thing that you can write down. And so this is not quite, well, this certainly isn't the Mikhalkin-Zharkov thing, but it's, the definition is sort of close and I don't know, it works. But this is very unsatisfying, just some big formula. So there's a more reasonable explanation for this guy.
This guy is like equivariant under the...
Right. So...
I guess you have GL and you have some translation.
Yes, indeed. And so this guy is equivariant under both. But so this is also slightly different from Mikhalkin-Zharkov. You can write down a version of this which isn't equivariant. And actually the non-equivariant version... So...
Sorry, what was BQ star?
BQ star is the dual bilinear form of BQ. Because I just mean plug the same thing in twice.
The quadratic form.
Okay. Right. So there's this question about what equivariance thing. So is this? I mean, should your theta function be a function or should it be a form in some sense? Should it, like, what should the co-cycle condition be? And here you get a bit of a choice. And so the Mikhalkin-Zharkov thing, this is really a form of a function. This version we've essentially cheated and forced it into being a function. So it is actually equivariant under both things, so it really descends. And so that's what you wanted. In order to make these true, you need it to be a function. On the other hand, if what you want to do is, if you want to play this game, where you want to write down a section of this tropical bundle, the tropical bundle isn't the trivial bundle. And so then you really want the version that's a form rather than a function, and it's a slightly different version. But anyway, this is all horrible. So, alternative. So Mikhalkin-Zharkov to get this was linear theta trop, which we'll call theta trop 1, and then repeat after expanding the lattice one over n times the lattice. So you can repeat that. So this gives you a piecewise linear thing, and then you can repeat that definition, and you get a new piecewise linear thing where the domains of linearity are smaller. And you can keep repeating this. Take the limit. And modulo this slight form versus function thing, which we can maybe not worry about too much, then you recover this definition. So in some sense, this is sort of the natural continuous thing that comes out of trying to do Minkowski-Jarkov's construction, but where you keep refining the layers. Okay, so I used my, was I going to say, I do have one more thing.
You have 15 minutes, I thought.
I have 50 minutes. I don't have 50 minutes of things to say. I was told I could use between an hour and a quarter, and I planned an hour. So I've overrun slightly, so that's okay. So I wanted to comment a tiny bit about how to prove these things. So somehow it's a long paper, and a lot of the effort just goes into actually defining the objects, like setting everything up to work. So proving, like once you've managed to work out like exactly what the right log line bundle here is, and write down the conical function, and proving that this thing is a section of that is pretty straightforward, and proving the purity is even easier. So a lot of the work then goes into the just to make sure everything's defined. The main exception to this is this Zariski closure theta bar thing. That's sort of the nastiest object around, because forming Zariski closure doesn't commute with base change or anything. So there are a few problems. So forming Zariski closure doesn't commute with base change, and moreover, when you talk about base change, you have to think, do I mean normal schematic base change or log base change? It's all kind of a complete mess. So the only thing which saves this really is the fact that this theta bar is a divisor, and so you can check equality divisors away from codimension 2. So you can somehow throw out the locus where all these problems are actually difficult. And then you're on a much more reasonable space, and you can actually prove things about this risky closure. So there's a question which comes out of this, I don't know the answer to, so maybe I'll leave this, which is, so if you take any G, so A bar is with or without the prime, is this thing. And this is, if the answer was yes, then it would have somehow shortened arguments here. We know that it isn't flat with reduced, so there's a very nice combinatorial condition for being flat with reduced fibers, and this condition is not satisfied. So it's not flat with reduced fibers. So it could be that it's flat and doesn't have reduced fibers. We know that it doesn't have, I would say it could be that it has reduced fibers and flat. We know that's not true. We know that not all the fibers are reduced. We know that it's flat up to G is 5, I think, but we don't, it's one of those things where beyond G is 5 or 6, it all comes from pathological. I have no idea if this is true. I kind of suspect it's not, based on the experience that with abelian varieties, like, if there are things that sort of you can only prove up to genus 5, it's normally because they fail beyond that. I don't know. This is no intuition.
Can you subdivide and then do, I mean, the standard procedure for the semi-stable reduction?
Yes. So, I mean,
why do you care about the particular model?
Because this is, I care about this particular model because this is one that I can actually write down in some sense. It's true that there are existence results about you can subdivide, but this feels to me very inexplicit. In particular, it wouldn't really help with this theta bar thing, because if I want to control the risky closures, then blowing stuff up is a very, I don't know, like, is not a healthy way to start the argument somehow. So I wasn't able, like, if I knew this was flat, it would have shortened the proof about this theta bar, and knowing that it's flat after a blow up wouldn't have helped me.
What do you use for G less than 5 to know that's flat?
Okay, so we know that it's equidimensional, so all fibers have the same dimension. So in low genus, things are smooth, and you use miracle flatness. In higher genus, it comes down to the fact, so up to genus about 5, it's flat with reduced fibers, and that comes down to the fact that every Delaunay cell is unimodular, I think. There are these examples of non-unimodular Delaunay cells, and that tells us that the flat with reduced fibers condition breaks. And there is a combinatorial condition just for being flat, but it's much more complicated, and I don't know how to check it in these examples. One thing that one could do is just, if one had a big computer, one could just like start writing down random cones in genus 6 and see if they're flat. I mean, there is a very explicit condition. Probably the answer is no, and your computer would, I guess, eventually find it. But I think we don't even know how many cones there are in genus 6. It's hundreds of thousands. But I mean, you could just like pick some at random and start trying. Then I guess if it's generically not flat, you'll find one. And if it's mostly flat but just a few cones fail, you maybe won't find it.
So your question is for the normal second Voronoi fan, not like some stacky version then.
Right, so Phil is hinting at the fact that you can replace these things with some root stacks such that it does become flat with reduced fibers. And this is indeed super useful, and we use that here. And maybe that's just what we should all do anyway. We should just replace these with root stacks, and it's flat with reduced fibers, and everything is happy. But there is something kind of appealing about like The only ones that we can naturally write down.
Is AG bar simplicial or not?
No.
So that's, okay. So it's not automatic that we will use that.
Generalized.
I mean, you
And
can
it just means like, you just mean replace the lattice.
Yes, sorry, I just mean replace
That's
the
not-
lattice by this other thing. I just mean replace the lattice by a sublattice when I say, sorry, I don't mean some more.
Can you repeat why the flatness was important? Like, what did you use?
Well, we didn't because I don't know. But it would have been useful for understanding this risky closure. So in particular, what you can do is you can, so if you, I mean, it's about the push forward, so this L bar, like this, like the high lower star of this thing. We know the cohomology on test curves. This is a computation of Alexeyev and Nakayama. And so we know the cohomology of this L bar fiberways. But we like to then use cohomology and base change to deduce stuff about what the cohomology looks like. And without flatness, we can't do that. But I mean, it's a fair question. Maybe, I mean, I'm not saying this is like important. It just seems like a sort of kind of an obvious question that we don't know the answer to. And it has a nice combinatorial, it's a completely elementary combinatorial question in some sense that we don't know the answer to.
Is it clear how this looks like after restricting to the closure of the Torelli locus?
I mean, I think on the matroidal locus, of which I am definitely not the right person to talk about, on the matroidal locus, everything is nice and flat and blah, blah, blah. And the matroidal contains Torelli. Is that a...
Yeah.
Yeah.
So the answer is yes.
The answer is yes. On the closure of Torelli or whatever, everything is nice.
So I think you already said, but every cone interlocalization of the universal family maps onto a cone downstairs?
Yes, so equidimensional.
It is combinatorially equidimensional.
Yeah.
So it really is the change of lattice that you're worried about.
Yes, exactly.
Okay, so Sam tells you, yeah, yes, you should change your lattice. Stack it.
I don't know. Yeah.
So that's a different question.
Yes.
With this intersection theory, that means if you take the top power of L, you get some real number
Yes.
as a function of G.
Yes.
Are these supposed to be rational numbers?
I probably not.
Well, you don't know what anyone is, like even below genus one.
I mean, I presume that in genus 1 I should know. In genus 1 I don't know because I'm just
But there's
incompetent.
is there any limit in genus one? Maybe it's
Yeah, so maybe that's I mean, even in genus 1, so in genus 1, the
it's going to be
torso...
like 1/24, right?
So this theta square thing isn't the zero section in genus 1. I mean, you take the zero section and then you add on, I mean, because the zero section isn't pure, so you have to add on this correction, which is some sort of quadratic function on the...
I used to have to keep going to keep splitting
Yeah,
more and more.
indeed.
So maybe it is that. Maybe it's a good concept. So is it also well defined if I take this
Power of L and the power of the total boundary. So I mean, L to the A and the total boundary to the B, that's not a number of total boundary.
Yes. It might be 0. I mean, the calculation that is, of course, very tempting to do is what's theta to the G, but that's not a top dimensional. So yeah, and I, as you can tell, haven't explored what these top things actually are.
Should we thank David at least? Any more questions?
To what extent is LC some kind of an object of an abelian category, some kind of thing you could take cohomology of?
I mean, one thing, so the question was, can you take cohomology of these things in some sense? So one thing you can do is you can say, well, take a piecewise linear approximation of C, and then take the cohomology of that line bundle, and then refine the piecewise linear approximation and hope that what you get converges or behaves in some reasonable way. And I think if you take a random element here, then the answer is going to be no. Those probably won't converge in some sensible way. I think that For certain nicely chosen guys, like if this is convex, then you've got a much better chance that if these are convex and you choose your approximation as to be like below it, then I think there's a much better chance that it actually converges to something. We've done some calculations with the Poincare by extension and pushing forward things, and it seemed like it actually was eventually constant, even the cohomology. But the general picture, I don't know. I would love to understand that.
One more. So the actual tropical theta functions wind up being like ratios of of polynomial functions, right? Some kind of.
Well, is first and second semantic polynomial things with cross?
I don't know. Right.
Oh, is that?
Is it okay? Maybe this is for later.
Yeah, I think so.